Hey, welcome to Wagner Academy as we take a look at 4.6 isosceles triangles. This is something we've learned about before, at least what isosceles triangles are, but now we're going to learn a little bit more about them, look a little more in depth into what's special about them. So let's make sure you use those extra examples in your book for extra help, and let's get right into it here. So we've got, for this first one, this is the isosceles triangle theorem, the big one, for one of the two big ones for this lesson. So the isosceles triangle theorem, and there's a follow-up lesson in between 4.5 and 4.6. They have some theorems in there, so this jumps to 4.9, so don't get confused by that. And then over here we're going to have what is the converse of that same theorem. So the converse of the isosceles, I'll abbreviate isosceles triangle theorem like this, and that is 4.10. So the isosceles triangle theorem says that if you have an isosceles triangle, if you start with that, which is exactly what we have here, then you can say that these angles are also congruent. So these are called the base angles right here. So we can say that if this is true, in this picture it happens to be true that AB, segment AB, is congruent to segment, I was going to say AC, but BC or CB, either would work. That being true implies that the angles, the base angles, are also congruent. So angle A is congruent to angle C. And my intent here was actually to put this in red right here. So this being in a different color. Come on, there we go. So I'm going to put that in red here and here. I think that's a valuable thing to do because we're saying if you start with this, then you can prove this red stuff is true, the extra stuff is true. And then over here, the converse, if you switch these things around, these two statements around, that's the converse. That's what we do with the converse, thinking back to chapter 2. So we can say, in this case, we have different letters, so we can use the letters that we see there. So we would say angle D congruent to angle F. If that is true, then that implies that this is going to be true, that it's an isosceles triangle, that you have two sides that are the same length. So I'll put that in the different color, and then I could say here that DE is congruent to FE. One more thing to add to the picture to the left here, I did want to say what these things were. So this right here would be the vertex angle. And then here we have a base angle. And over here we have the other base angle. So the base is AC for this isosceles triangle because it's across from the vertex, or across from the vertex angle, I should say. And the base is always going to be that non-congruent side if we have an isosceles triangle that's not also equilateral. So it's this either longer or shorter side compared to the two congruent sides. So let's use these two theorems now to say some stuff about the triangles that we see in some examples down here. So determine the measurements below. We're going to find the measure of angle S in this one, and we're going to find the distance from M to T on this one. So it looks like the measure of angle S, well, I could say some other stuff about this. I'm going to use my different color now, so this is what was started with in here. I could say this is true, although that's not really needed to solve the problem, but that would be true. This is the same as this. So we have an isosceles triangle. However, I notice this one's 90, and I can prove based on the fact that this is an isosceles triangle. Not real happy with that arc mark, but we'll just go with that. So this one's congruent to this one. It is an isosceles triangle, so that means this applies, this theorem right here. That means these base angles are congruent. The base doesn't always have to be in the bottom. It's just across from that vertex angle. It's the side other than the two congruent sides. So here's the base in this case. What's the measure of angle S? Well, if I know the triangle angles add up to 180, and I know this one's 90, I can just say that this one is going to be 90 divided by 2. This is what's left over, 90 degrees right there for those two. That was something we learned about right triangles. These two had to add up to 90. So we could say that this is 45 degrees. So the measure of angle S, this is actually something called a 45-45-90 triangle, which we'll learn a little bit more about later. So let's make this statement over here that angle I was congruent to angle S by the isosceles triangle theorem. So that was this one right here. We started with an isosceles triangle. The sides were congruent. We can prove then that the angles are the same based on that theorem. Over here, MT, looks like we have the converse now applying. We have the angles given to us. That means these two sides are going to be the same, the legs of the isosceles triangle. So I can prove based on this theorem that this would be congruent to this. And this one's very straightforward. If this and this are the same, and this one's 10, then this one also has to be 10 centimeters. So what's the answer going to be? It's going to be 10 centimeters. And so on this one, we used the converse of the isosceles triangle theorem. So we've got ME is congruent to MT. And I'm just writing this down so that when you look at this later, potentially, you know where this came from. So it was by the converse of the isosceles triangle theorem. So that's why that was true. Looking at now example 2, I think you're going to feel wicked smart after doing this one. It's going to bring together a lot of things we've been learning throughout the last couple of chapters especially. So let's start with what we're given here. We're given this information. If segment SM is congruent to segment ST, so I'm going to use my normal color for this. So SM is congruent to ST. All right. That's true. What else is true here? We've got AS is congruent to AM. So that would be this one is congruent to this one. Okay. Measure of angle SMH is 32. So connect the dots. SMH, the angle that it draws, this one is 32 degrees. And it says also that the measure of angle AHS is 64. And that also equals the measure of angle HAS. So AHS, connect the dots, this one's 64. And HAS, connect the dots again, HAS, that means the angle it draws right there is also 64. So what is the measure of angle MST? So this big top angle here with the big triangle, the big outside triangle. So how can we figure this out? So I'm going to now get out my different color. I would recommend doing the same thing. I think that's a good idea here. So I'm going to start with, well, I'm going to look at this triangle, MAS, and I notice that this one's 32. This is an isosceles triangle, so based on the converse over here, or not the converse, but the regular isosceles triangle theorem, I have an isosceles triangle, I can say the angles are the same, the base angles. So I know that this one would be congruent to this one over here. So I can say this is 32 degrees as well. And I'm going to, just off to the sides here, I'm going to write down the reason for each thing I'm saying. I'm going to put a little 1 next to this, saying that was the first thing that I found out. I could have gone and found something else that was true. There's going to be another or other logical ways to do this problem, but this is just the way I'm seeing it first. So we use the isosceles triangle theorem with, you can write W/ as shorthand for with triangle MAS. So that's where that 32 degrees came from right there. So this is 32 degrees, this is 32. So from here, let's see what else I could say. I notice that this big triangle on the outside is also an isosceles triangle. So I'm going to use the same theorem, the isosceles triangle theorem, with the big triangle, with MST. And that would allow me to say that this one is also 32 degrees. So right here, This was step 2 for me. I'm saying that this is true by the isosceles triangle theorem with triangle MST. Okay, so what I'm really trying to do here, MST, that's this big angle up here, that angle MST. I'm trying to find this one, and this one. If I know all three of those angles, I can just put them together and get the angle measurement I'm looking for. So I can't just assume that this angle and this angle are the same based on how it looks. I have to actually prove it. So I'm going step by step in a logical sequence here. What else could I say is true? Well, it looks like I've got 64 here and here. These clearly are making linear pairs with these two angles right here and right here. So I could say both of these are 116. That's just 180 minus 64. So I'm going to circle both of these and use the same reason for that one. So this was step 3. And again, there are different orders you could go in to solve this problem. You may be even able to find a totally different way to solve this problem, or a totally different set of steps. But a linear pair here would work to show you why those two angles are what they are. And now I want to use something we've been learning in the last couple lessons before this, those triangle congruence theorems and postulates. So I have angle, I'll start with this one, 116, this angle, this 32, and this side. Angle, side over here is congruent to this angle, and this side. So I have angle, side matching with angle, side. It's a non-included side. It's not the side in between those two angles. So that's angle, side right there. That would allow me to say, in turn, that this one would have to be the same as this one, because this is a corresponding part of congruent triangles. If we use angle, side, that proves that's true. So that's a fancy way to figure out that that one is 32 degrees. So step 4, we can say angle, side, that proves those two triangles are congruent. That implies that corresponding parts of congruent triangles are congruent, CP, CTC, and that goes along with triangle. We said this triangle over here, triangle MAS, not MS, MAS, here we go, and triangle in the same corresponding order, MAS would match up with THS. So I'm just about there. I got this one now, I got this one, and I just need this one. This one's pretty easy to figure out, I think, because look right here. You got 64, you got 64. That one then would have to be 180 minus those two put together, and 180 minus those two put together, this is 128. That would leave you with 52 degrees right here. So let's make a note of that. Up here, step 5, this was the triangle sum theorem. Or in other words, they add to 180, the three angles, and that was with triangle, this one right here. You could put the letters in any order, but I'll go with AHS. So feeling wicked smart right now. We got 32, 52, and 32. You put those three together and you've got what you're looking for, the measure of angle, MST. So I can say, therefore, based on all that stuff we have up here, the measure of angle MST is going to equal 32 plus 52 plus 32, and that ends up being 116 degrees. And then for example 3, we got to talk about one other thing first before we do that one other set of things. So this is a corollary right here, and this is corollary 4.3. It's the third corollary in this chapter, and this is a corollary 2. Remember, corollaries follow quite directly or quite quickly from particular theorems. This is a corollary to the isosceles triangle theorem, and so is this one actually. So a corollary 4.4 is what I have over here. This is also a corollary, something that follows directly from the isosceles triangle theorem. So what's this one say? This one, I'm just going to have you use your normal color for this, because it works in both directions. So if you have an equilateral triangle, that means you have an equiangular triangle. If you have an equiangular triangle, that means, conversely, you have an equilateral triangle. So equiangular and equilateral, they go together. So I'm going to circle this, I'm going to circle this, and then I'm going to put a double arrow in between those. So an arrow pointing in both directions. That's meaning that you can start here and go that way, or you can start here and go this way. This is an if and only if statement. So if you have an equilateral triangle, it's equiangular. If you have an equiangular triangle, it's equilateral. So a triangle is equilateral if and only if it is equiangular. That's another way you could say that. And then for corollary 4.4, this one, we start with an equilateral triangle, and then I'll get out the different color for this part. That implies that these measures are all 60 degrees. And I think that kind of follows directly from what we said here too. If they're equiangular, they all have to be the same. It's just 180 divided by 3 then, but that is a corollary for the isosceles triangle theorem. So the equilateral triangle implies that you have all angles being 90 degrees. Or not 90. What am I saying? Oh no. All angles are, I'm going to write it down right, 60 degrees. There we go. They couldn't all be 90 because that would add to 270, and that's not a triangle, at least in Euclidean geometry that we discuss here. So example 3, assume that triangle BRC is an equilateral triangle, okay, and that measure of angle BNR is 90 degrees. So let's label that stuff in the picture with our normal color. So BRC is equilateral. That means that this and this side, and I'm going to put this one almost right there, but not quite. I'm trying to put it in the middle as close as I can to BC. So this is not saying NC is the same as RC, but I'm saying BC is the same as RC, which is the same as BR. And so from there, we also have that BNR, so let's connect those dots. BNR, that draws that angle out. It is 90 degrees right there. So I'm going to put that in the picture as well. Now we're trying to determine the measure of BRN. So that's this one right here. Measure of angle BRN is going to be, well, if this is equilateral, I know then, I'm going to get out my different color once again here. I know that this is going to be 60 degrees right here. And so is this, and so with the whole thing here. So I can label those things, and that's BRN. If that's 60 and this is 90, BRN should be pretty easy to figure out. We'll get there in a second. Let's write down again why this one was, though. This was the corollary right here, corollary 4.4. So that's why that is 60 degrees. You have an equilateral triangle. They're all 60 degrees. You could say the same thing about that one. I didn't really need to write this one down, but I definitely want to include this one. So look at triangle BNR. That's going to add to 180. That means that the measure of angle BRN would have to be 180 minus those two added together. Minus 60 plus 90. So why is this? What's the reason for that? This right here is the triangle sum theorem. So that leaves me with 180 minus 150. And so that means this angle BRN right here is 30 degrees. So why don't I put that in the picture now? This is 30 degrees. And I'll use a box for that because that was a portion of my final answer. And now let's find x. So if I know that this is 30 and the whole thing would be 60, because this whole triangle is an equilateral triangle, I know this and this put together would have to be 60 degrees. So I could say, another way to say that would be this. Measure of angle CRN right here would be 10x. It's labeled in the picture like that. And that would have to equal, since 60 minus 30 is 30, that would have to equal 30 degrees. And so from there, it's a simple algebra problem, I think. Just divide by 10, and you've got your answer. X equals 30. 3. Now you might have looked at this and said, find x, and then you were like, oh, there it is. Oh boy, nice try. No, find x, when it says to find x, actually solve for x, figure out what it equals. If you try to pull that on me on a test, I will laugh, and I will not give you any credit, but at least you will have made me laugh. So, example 3, there it is. Try the problem. Please don't just circle where x is. So example 2, if you don't know what to do, at least try. Example 2, example 1, we went through our 3 examples there. Make sure you use those extra examples in your book as well. Make sure you know these terms. And as always, you know what I'm going to say, right? Have a great day. All right, I will see you later for our next lesson.